This is a joint work with Peter Kissman, and even if it's a SOX talk, it's also about planning. So for those of you that were here last Tuesday, I presented a preprocessor based on S2 that is able to simplify the task, removing operators that it can prove that doesn't belong to any plan. It's very useful across many domains, but today we can go even farther. So here I am showing the DTGs of a tracker and a package in a typical logistic task. So we can move the tracker to every location and load and unload the package. So here you don't have any unreachable or dead-end state, so our preprocessor cannot prune absolutely anything. However, if you give me that problem, I can easily tell you that there is no reason why should you unload the package in any other location than the goal, and there is no reason why you need to move the track from I to G by the longest path. So all of these parts of your problem can be automatically removed. And of course, you might argue that why are we going to model problems like this? Well, the fact is that I don't trust the users of my planner, so I want my planner to be able to deduce this by itself. And for doing that, we are going to need two different ingredients. The first one is the merchant ring. It's a method to generate abstraction heuristics. And in merchant ring, we start with a transition system for each variable in our problem. So if we have 4 variables, we will start with 4 transition systems. All of them share the same labels that initially correspond to the operators of a planning task. And we have 2 operations. We can either merge 2 of these transition systems, but when they are too large, we need to shrink them by replacing them for abstractions of themselves. And then we can continue merging, and at the end we have an abstraction that can be used as an heuristic. Okay. The second ingredient is a written method for dominance pruning that computes a label dominance simulation on this partition of the merchant ring. So basically, it takes as input a set of transition systems, and you don't need to know the details, but what you need to know is that we compute a set of relations, and each of these relations has 2 parts. On the one hand, it gives us a label dominance, so it tells you whether a label is better than other in each of these partitions. And also, we have an state dominance, which tells you if an state is better in each of these partitions. What it means for a label to be better, it means that, well, everything that you can do with one label, you can do with the other. And for a state, everything that you can do from a state to reach the goal, you can do from the other. Okay. In this other work, we have used this information in order to perform pruning during the search. But here we are going to use the same information, but to simplify the problem before starting any search. Okay. But before that, I want to talk a bit more about merchant ring. Merchant ring has been used to generate heuristics, but the whole framework of merchant ring is not limited to that. Actually, for this dominance pruning, we have used merchant ring, and we are not generating any heuristic. The point is that Silva and Martin and Malte, in their 2014 paper, they re-explained the way in which we understand merchant ring, and it becomes clear that it can do much more than generate heuristics. So basically, in merchant ring, we have this set of transition systems that initially are the variables in our problem, and they implicitly define a global a global transition system, which is the product of all this. This has exponential size, so it cannot be represented, but they implicitly define this global state space. This somehow reminds of a planning task. We have the variables that implicitly define your state space, so it's basically the same. The point in merchant ring is that we can perform transformations to these transition systems, and this will have an effect on the global state space. So we have a bunch of operations that we can perform here, and this will transform our planning task. What's important is what guarantees these operations give us about the transformation that they do in our task. So basically what we are going to do here is to define a new transformation that is not tailored to generate abstractions, but for something else. This transformation removes transitions from each individual transition system, which This means that we are going to be removing transitions in our state space, but it has the warranty that it's going to preserve the optimal heuristic value of every state in our state. So basically, it's going to preserve the goal distance for every state. Okay, so first thing that we want to do if we want to do a transformation of planning tasks is to define which are the guarantees that we want to hold for this transformation. And the basic guarantee that we want here is what we call plan preserving, which means that on the one hand, we don't want to add any new plan to the task. And on the other hand, we want to preserve at least one of the optimal plans of the task. Why do we want this? Well, if we have this guarantee, then we can search the modified problem instead of our original problem, and the solution for the modified problem will be a solution for the original problem. Okay, we have that some of the operations in Merchant Ring are plan preserving. For example, removing unreachable or dead-end states, it's plan preserving. Also by simulation, it's plan preserving. And in this paper, we introduce this new operation that removes transition, so obviously does not add any new plan. And it's globally edge preserving, so obviously it preserves at least one optimal plan. Okay, so the definition of this pruning is quite easy. We can prune any transition that is subsumed by other. So when a transition is subsumed by other, well, a transition is subsumed by other, basically if they have the same source state, the subsumed transition has, or the transition that subsumes the other transition goes to a better target state, it has lower cost, and the label dominates the label in all the other transition systems. So basically this means we go to somewhere that is better, we spend lower cost to do that, and the size effects on the rest of the problem are better. Okay, and well, this allows us to prove that if you remove the transition that is subsumed, then well, you preserve the optimal plan. Okay, so let's go back to our logistic example. We have this graph with the track movement, and we can, using this information, we can see that going from I to A is worse than going from I to E. So we can remove the transition from I to A. And the same can be said about going from G to D. So well, putting two transitions in this graph doesn't seem too much. However, if we now run this unreachability analysis, we get the desired pruning. We prune all this part of the state of the movements of the track. Okay. So well, one more example. Here we have two partitions of our problem, and here is the global state space of the product of these two transition systems. And the black transition at the top, we can remove it because it's subsumed by the blue transition, because in the rest of the problem, the blue is better than the black. This removes one optimal plan for our planning task, but it has the property that we desire, that at least one optimal plan is preserved. By the same arguments, we could remove this transition, removing this optimal plan and preserving the other. This example is also useful because it shows that whenever you remove a transition, this label dominance and state dominance might change. So what we will do in practice is we will not prune any transition if this might happen. Okay? So once that we have a transformation, we can do several things with it. As I have pointed out before, you could search the transformed task, which is smaller than the original task, and use that as a plan for original task. However, this search task is represented as a merchant ring transition system, and this could be quite an implementation overhead. It will require to implement all the search algorithms and all the heuristics. And we wanted to test this idea in a simpler setting. So what we are going to do is basically see which operators have been completely removed from the task P prime, remove them from P. So basically we get a task that is in the middle of the two, and we will search the original problem but without these operators. And of course, the operators are not only not considered by the search, but also not considered by the heuristics or anything else. Okay, and the other possible use of this, of course, is to generate merge and shrink heuristics. However, if we use the heuristic for our task P prime, for our task theta prime, instead of for inform the search in the state, in the original state space, this will be a not admissible heuristic. However, this is not bad news. Actually, it's a feature of our technique, because it means that we are going to expand less states. And even if your heuristic is not admissible, it fits one property that was defined by Ernst Karpas and Carmel Domzak, that is globally admissible. And this property is sufficient to guarantee that A star will return optimal solution. So basically, we get additional pruning from our heuristic. Okay, one side note here, you cannot perform any shrinking other than by simulation before doing the transformation. So all this requires that, that your transformation, your transition pruning is performed before applying a shrinking. Okay, another use that you might have for your dominance relations that related the states in your transition systems is to perform a shrinking. So we define similarity shrinking and a shrinking every pair of states so that both are better than than each other. This transformation has nice theoretical properties. It derives perfect heuristics, so the same than by simulation, and it derives a smaller abstraction, so it's quite good. However, in practice, it's a bit redundant with the subsumed transition pruning. So we saw that if you perform subsumed transition pruning and compute the by simulation, then you basically get the same in almost every case. Okay, so we ran some experiments, we ran several configurations. The result that I am going to present here perform incremental computation, which means that we recompute this label and state dominance relations in every step of the merge and shrink, so after every merge. And we disable label reduction and by simulation and shrinking. And this is because label reduction and by simulation and shrinking doesn't always help to get more pruning. Also, it's important to know that, well, the preprocess is successful in most of the tasks, but not in all the tasks. This is quite expensive, and it takes several hundreds of seconds in some tasks. This means that it is suitable for optimal planning, where all these tasks that you cannot preprocess, you cannot solve them optimal anyway. But for satisfying planning, we have to improve the current implementation and the current parameter configuration in order to be able to use that. So, well, let's take a look at the results. If you look at the results of the merge and shrink heuristics, it improves in the number of node expansions, and it also improves the time. So, in general, it's an improvement over current merge and shrink heuristics. But the most interesting stuff is, well, okay, this can really simplify your planning task. And the answer is yes. In several domains, it performs quite significant pruning. There are a couple of domains in which it gets even a 90% of operators removed from the task. And well, of course, here is a selection of domain. It's not like you get this on every domain, but there is quite a number of domains where it really helps. The first column is here our new pruning. H2 is the H2 preprocessors that I presented the other day, and as we can see, the combination of both has a pretty good synergy. If you look at the coverage under the LMCAT heuristic, we can see that it helps in several domains, and well, using both methods, you can very significantly increase the coverage of LMCAT. And actually, we also integrated it in. One advantage of these preprocessing techniques is that you can include them in every planner. So we tried in the state of the art, in the current state of the art, which is symbolic by directional uniform cost search, and it improves a bit, not as much as in these other planners, because well, there is less margin for improvement. Finally, we compared against other irrelevance pruning methods. And, well, the results are well, the main pruning method that we found is the method by Patrick, Malte, and Anders. And, well, it works on the DTGs of the variables, contrary to us analyzes paths instead of using this simulation and only looking at one transition. But it has the important limitation that the current version, it's only applicable to unary domains. And well, as we can see, they have similar performance in all the domains where it is applicable, except on Blosswall, but it has to be said that in Blosswall, we are using different representations of Blosswall here, so the results, well, are not really comparable. Okay, so to finish my talk, the three take-home messages. The first message, I think that merchant ring is a very good framework for transformation of planning tasks, not only to generate heuristics, but for much more other applications. The simulation relations can be used for dominance pruning, of course, but they can be also used to perform this pruning inside the merchant ring, and it has quite good result. Similarity shrinking is a nice application with quite nice properties, but less useful in practice. And finally, most of the benchmarks that we are currently using in planning has a great amount of irrelevance. So I think that a study of irrelevance pruning techniques is quite interesting for future work. And particular future work to extend our work are extensions that allows us to infer more knowledge about the planning task that can be used to simplify it. Considering paths instead of looking at just a single transition, of course. And as I was saying, include new types of transformation into this merchant ring that can allow you to do different things. So, well, thank you for your attention.